everyone. Can you hear me? Okay. So we are going to talk about eBPF. So before coming over here, how many of you have heard about eBPF? Okay, great. So I'll be giving a very 101 kind of a talk. So we are not going to go deep because eBPF is a very vast subject, and it would require quite a lot of hours to dive deep into that. So this is the agenda for today. So we'll be looking at the struggles of the typical kernel developers, and then what the superpowers that we can get with adopting eBPF, and a little bit of under the hood of eBPF, and a couple of demos where we'll be mostly concentrating on, and then we'll be wrapping up with hooks and maps, again the concepts of eBPF. Right. So any kernel developers here? Any Linux kernel developers? I would like to hear some stories from them if there are. Okay, fine. So we'll see why the Linux kernel struggle is a very real story. So these are, again, I'm not going to read through this. You can just read through this, but the problems with the typical Linux systems, do you know what is the latest version of Linux, or what version you guys are using? That's the case, right? We don't care. We don't know. We don't care about what version we are using. It could be 3.8, 4.5, I don't know, 6 plus version, right? So we don't care because it's very rarely that we upgrade Linux versions, right? And actually, whenever there is a need of an upgrade for any of our use cases, right? Whether that could be an application or it could be anything that is running on top of the Linux kernel itself, right? Whenever you require any change and you submit any feature request, do you know how much time it will take for that feature request, even if it is accepted, to come into production? Right? Months, days, months, probably many years, probably a decade or so also, right? So it's very difficult. And also imagine that, of course, after a few years, the feature that you are looking for has ultimately landed into a particular version of Linux. And by the time your application might have been upgraded, right? You might have added more features. Now you will go to the developer and say, the Linux developer, and say, no, I need more features, right? Or the feature that you have given me probably might not be suited for this decade's audience, right? We require more features. And then you go back and again submit a feature request. Or probably you write your own Linux kernel and want to patch it and want to come up with everything else. So it's a very painful process, right? So this is the typical kernel upgrades, right? After patching or after developing some part of the Linux kernel, it's a very painful process. Of course, not everything is doom and gloom. There is a concept called as Linux kernel modules, also called as loadable kernel modules. So this is sort of a way where actually, without breaking your heads or your minds, what you can do is that you can do small developments and sort of extend the capabilities of your kernel without making a major upgrade, right? So you can see there are some goods, but you can see that the not so goods dominate a lot, right? Again, I'm not going to read a lot on this, but the very wonderful thing about these kernel modules is that they are pluggable, right? So you can plug in whenever required. If not required, you can plug out. And you don't require any reboots if you apply these kernels. But again, the problem with these kernel modules is that the last one, which I mentioned as the good, where you get broad access, if not done properly, that will be sort of a nightmare for you, right? So if you change one single line of code, assuming that, okay, I'm bringing a new feature in, probably it might break somewhere else, right? How many of you know the blue screen of death? A lot of us, right? Many times, at least once in our lifetime so far, we might have gone through that experience, right? So thanks to these kind of experiences, right? These are the ways which we can get those experiences as well, right? Again, I'm not going to read through all of those not so good, but yeah, you can check those. It's not, there are no safety checks, right? Unlike eBPF, which has a very wonderful, beautiful verifier, we are not going to deep dive into that, but yeah, that feature is there, we'll look into that. And also it's very hard to debug and trace. You know, if something goes wrong into your kernel module, it's very hard to debug and trace. And of course, there are no tight security restrictions. Yeah, and then very inflexible life cycle. And why we need a better way? Again, I wantedly, you know, mentioned it as a fintech company. Didn't want to take the name of that company. But yeah, you can read this. One of the companies, they wanted to customize a net filter module, which is used basically for tracing packets, right? But when they were trying to apply this patch, they had to recompile their entire kernel for various reasons, right? And once you recompile your entire kernel image, what you need to do is that you need to apply that on all the nodes, right? N number of nodes, hundreds probably, right? In some organizations, probably thousands. And yeah, you don't want to be that developer sitting there, right? And what we require is a very safe execution in the kernel, right? This execution should be sort of a sandboxed run. It should not be leaking outside that boundaries. And then it should be programmatical, because we all as developers would love to program anything. And of course, you shouldn't be having any crashes, or you don't want to have any reboots. And of course, you want to have a very full observability, what's exactly happening. Okay. So this is where eBPF comes into picture. And I want to introduce you my co-presenter for a minute, who would give a very quick intro of eBPF, and then we'll continue. Is this working?
Studying in second class. Today I'm going to talk about eBPF. eBPF stands for Extended Berkeley Packet Filter. Suppose this is a computer. In a computer you will have Linux. In Linux there is a small place for eBPF. This up part is called user space. In user space there are apps, and apps connect to eBPF. Thank you.
Thank you. All right. I don't know how much you guys have got with that. So let's continue. Never forget. All right. Again, I'm not going to read all this theory, because I really want to jump into some demos. But before that, I want all of us to be on the same page. So how many of you have heard about BPF? eBPF is fine. BPF? Okay. BPF was sort of an ancestor for eBPF, which stands for Berkeley Packet Filter eventually, right? So the purpose of BPF was just to track the network traffic, and it was having very less functionality. And that is when eBPF was born. It was born more than a decade ago. What I meant to say is here is eBPF, and they have extended the capabilities to a lot, so which we will be seeing. So you can, the most important thing here with eBPF is that you can write programmable kernel hooks, which we will be seeing what they are. Again, I'll skip all of this. Yeah, so this is what you can do with eBPF. You can have a full observability. You can also have security baked in, networking. I'm sure a lot of you, how many of you are using Kubernetes? Great. How many of you are using Cilium? Calico? Flannel? Anything else? Pixie? Great. Okay. So Cilium is the company who created, I mean, it's not a company, it's a product basically. The company who created Cilium is Isovalent. So they are the creators of eBPF. And all their product line, that is Cilium, Tetragon, Hubble, are all powered by eBPF. And believe me, it's a super powerful tool, which we will see eventually now. So Kubernetes is powered by eBPF, you can say indirectly, with all these tools. And then when you compare eBPF with kernel modules, again from a safety perspective, eBPF runs in a very much sandboxed environment, whereas with kernel modules, you get full access to the kernel, which could lead to be a very potential dangerous thing. And deployment, with eBPF, you don't have to reboot. And with observability, as I mentioned earlier, unlike kernel modules where you have very limited observability, with eBPF you get very deep and programmable observability. And of course, the performance, you can get deep peak performance when it comes to eBPF. Right. So this is the architecture. Again, we will look into this. So basically what you do is that you write a C program. Basically, all the kernel modules or the entire kernel, as you know, is written in C, right? And what we do with writing eBPF programs is that there are two parts of eBPF program. One is which runs inside the kernel, and the other that sits in the user space. So the one which is sitting in the user space, you can write in any programming language of your choice. So you can write in Python, you can write in Go, you can write in Rust, or you name it. So once you write the eBPF C code, what you do is that you compile that. Of course, there is CLang or LLVM. There are many compilation tools that will help you to convert your C code into eBPF bytecode. And once that is done, you will load that into the kernel, and before getting loaded, it gets verified. That is where actually I was speaking earlier, that verifier plays a very crucial role. But when you do the same with the kernel module, there is nothing of that kind. So you are on your own. And once verifier checks, it again, just-in-time compilation is an optional thing, but it will improve your eBPF program's performance a lot. And once assume that the program that you have written, you were able to load into the Linux kernel. Now, once you load, it becomes an orphan unless there is some kind of hook that attaches to this program that is running. And that is where actually hooks comes into picture. Again, there are hundreds of hooks. It's not possible for us to go through all of those. I'll be showing a glimpse of a couple of these hooks. And once you have that hook attached to that, what happens is that there will be system calls. You can have n number of your applications running. Whenever these applications that are running, gets attached to one of these hooks get triggered, and then eventually your eBPF program runs, right? So we'll see this into picture, and then we will end up with the user space, the maps, which are used to communicate between your Linux kernel, where actually your eBPF program is running, and then your user space applications. Right. So enough of the theory. So let's get started into the exciting part here, hopefully. So we'll have two things. One, I'll be using a Python framework here, which I don't like it a lot, but yeah, have to use some framework to show the features. And then I'll also be showing it in pure C language. Is it visible? Let it increase. Is that fine? Is that fine? Okay, I might not be able to see now. Okay. Is it visible? Okay, fine. So I told you that any eBPF code that you have will be having two parts to it. One is the eBPF code itself, that is nothing but the eBPF program itself, and the second one is the user code, which is nothing but that runs in the user space. I mean, don't take me literally, because we are writing and running it from the user space, but the thing is that whatever that you see it in stringified way here, this is nothing but the eBPF code, right? So this gets compiled on your user space, but eventually you will load this into the eBPF virtual machine where actually the code runs. Okay. So very quickly I'll run down this. How many of you are using C today? Any? Okay, fine. So please correct me if anything is wrong, because I don't use C. Okay. Right. So hash include, we are using the header files here, and then what we are doing here is that we are creating a struct, and then these are the things that we'll be creating inside this function. So this function that you are seeing, right, will be eventually getting deployed into the eBPF, and this is what we will be hooking our events with. Okay. So again, what you are seeing here, this lot of functions that you see here, right, are built-in functions that are given out of the box by eBPF. And one important thing that I have to mention here is that this is not a complete C language that you will be using with eBPF programming. This is called as limited or restricted C. Okay, because you can't write infinite loops here. Like you can't have a while loop without bounded, and you can't map a variable to a null address. So those sort of things you cannot do, because if you do that, then the verifier will block you deploying this. Okay. Fine. So what we are doing with this program, right? I have a README also here. I'll quickly bring it out. Right, this is what actually it does, right? It traces every system call invoked by whenever you give ls on a terminal. What it will do is that it will throw out, or it will spit out some kind of information onto the screen which we'll be seeing. Okay. Right. So, okay, my bad. Let me start with an. All right. Yeah, anyhow, I started with this. I wanted to start with a different program, but yeah. Again, one important thing here before we start is that this BCC that you are seeing, right? This BPF is nothing but it's a wrapper around your C-based eBPF source code. Okay, what it does, what this particular eBPF program does is that whenever you issue a command, like here you can see that this is hard coded for the command ls, but you don't need to hard code it. Just for simplicity, I have hard coded it, right? But what this will do is that whenever you hit ls anywhere in any of your terminals or anywhere in your system, it will capture that. Okay. And what we are doing here is these two things. So this particular line that you see here is the user space code, right? This is the actual kernel space code, and what we are doing here is that we are passing this string as a string to this function, that is BPF, and what this will do is that it will verify, it will compile basically this particular C code, that is eBPF code, and then it will through the BPF system call, it will send to the Linux kernel, Linux kernel in the sense to the eBPF basically, and then it gets deployed over there, or it gets loaded over there. So that's the first part, and it does a lot of things out of the box. Okay, once your eBPF code is loaded inside the Linux kernel, as I said earlier, just leaving it here till here, your eBPF program will become an orphan, right? So what you need to do is that you need to attach something. You can attach, there are a lot of attachments that we can do, right? There are K probes, there are user probes, there are trace points, which we are using in this example, and there are a number of things. So in this example, what we are attaching is this syscall, right? That is, whenever you enter the system in your terminal, whenever you enter ls, this gets triggered. And what we are doing is that we are hooking up with this function call. So this function is nothing but this function that gets deployed into your eBPF. Okay? And once that is done, again, the beauty of this is I mentioned in the theoretical part where I said maps play a very crucial role, because maps help you to send the information from your eBPF to the user space, like eBPF running inside your Linux kernel, to the user space, and anything that you want to fetch from user space inside your running eBPF code. Okay? So we specify that in this way. Okay? So even I'll show you the Linux source code as well, where you will be able to see all of these different types of BPF map types. Okay? So here we have mentioned perf buffer. So this is one of the map types, very performant map type. We have mentioned events here, and you submit this through these events, and then in the user space you will be able to capture that events like this. Okay? So this entire code you would be able to capture anything that is running with events. You see that in this function we mentioned that from the events I want to get the data. Okay? And this is what actually will be printed whenever this hook gets triggered and your eBPF code runs. So I think I'll give a quick run so that we'll be able to see. Okay, now our eBPF program started running. Now what I'll do is that I'll just run, I have opened a new terminal and I just typed ls. And by the way, quick question, if we run ls, how much output we are expecting? Is it one line, multiple lines? Any idea? Sorry? Just ls, nothing else. Single line. Right? These are the number of system calls that happens even when you issue a simple ls command, right? So from your user space, you are issuing ls. These are the number of calls that are happening to the Linux kernel. So the next time you issue ls, thank Linux, right? Okay, all right. So again, see, this is what actually happens under the hood of all your observability tools these days, right? It doesn't matter whether you are using Datadog, whether you are using X, Y, Z tools. Sorry? Broadcom as well. Yeah, big thanks, big congratulations for Broadcom for using eBPF, right? So this is where actually how you use eBPF. In a Pythonic way, right? But in reality, you don't use Python because it's not originally that performant, right? What people generally use is a framework called as AYA. I don't know how, AYA, however you wish to pronounce. So that's written in Rust. You write in Rust programming language. Or if you are quite good with Linux, with C programming language, you are good to use both your user space as well as your kernel space in C programming language. I know that Amit is showing 5, 4, 3, 2. So I don't want to take much time here, but very quickly I'll show one more demo and then we'll wrap it up. So I have another program here, which is like tracking a few system calls again. but here in this case, actually, you can see that I've written bunch of things here. We'll look into this. All that it does is that whenever you issue any system call, like ls or cat or etc., it again captures this, and again it shows onto the screen, not so beautifully, but in this case we'll see how it shows. Okay, let me go into. Okay, so these are all the, again, earlier if you remember, I told that I have hard coded, right? I have hard coded that it only shows ls. But now, without even running anything on my system, right, you see that I'm not running anything on my system. So these are all the background things that it is running. So it doesn't stop, it all depends upon your system to system, it varies again. Okay, now what I'll do is that, again, I don't know whether I'll be able to capture this. If I run ls here, you see that it is showing ls here, right? So this is your process ID, and I mean sometimes it if you go and check this process ID, by the time you say ps and give this process ID, it will be lost, because ls is not a long running process, right? Right, I think that's it for. I mean, again, I'll give a very quick glimpse of how it looks in C, and then we'll wrap it up. I won't run that, but I'll just show you. So this is how you write in C programming language. Basically, this is your eBPF code. Unlike in the other frameworks, typically where you will be able to hook it directly, here you cannot hook directly. So you will be using these macros. This macro is very important, because what you are doing is that you are hooking the trace point to this particular function. Okay, and then your user space code would be quite big here, because you have to do manually. You remember I showed you one command where I said that it's a BCC command, where I told you that it will compile and it will verify and it will attach, it will load into your Linux kernel, right? It's doing a lot of heavy lifting. But when you write your own C code, you have to do all of that on your own, right? So all of these things in the earlier Python code was handled by a single line of code, right? So you eventually, when you write your own C code, you have to take care of everything. Okay, so that is where people started using Rust, because Rust is, as you know, quite faster compared to Python, and also, it has got its own advantage. I don't want to go deep into that. I think I'll come back very quickly. We have ran through eBPF Python and eBPF from scratch, nothing but in C programming language. I told you that there are n number of hooks. We just have gone through a very simple hook, that is trace point. I thought of showing the kprobe hook also, but then I had to change my laptop at the very last moment, and then with each Linux version, this kprobe gets changed, right? If you think of using hooks, the best hook that you can use is trace point, because it doesn't change with kernel versions. Okay, and then eBPF map types. We have used one map earlier. I told you that we have used perf map, right? BPF perf map, but there are n number of maps depending upon your requirement you can use. Yeah, thank you for being with us.